Alright, in the last video we defined the payoff matrix for a game, and we mentioned that the ij entry is the payoff to the role player if the role player chooses his ith strategy and the column player chooses his jth strategy. Well, let's see how this works in another example. Here we have another game where the role player has two strategies and column player has two strategies. And let's see if we can analyze what's going to happen here. If you just look at the game, the role player is saying, wow, that 5 is good, but that minus 10 is bad. And the column player is saying, well, that minus 10 is good, that 5 is bad. Right. Now, if we look at this from the column player's point of view, he's always better off choosing column 2. Column 2, if the role player chooses row 1, column player is better off here because he gets the minus 10. And if the role player chooses row 2, column player is better off here because it gets a 0 instead of 2. So it stands to reason the column player is always going to choose column 2. Now what about the role player? Now, the role player is looking at this 5 and he's saying, well, I want to get that. But if he realizes the column player is always going to choose column 2, he realizes he'll never get the 5. If he tries for the 5, he'll get the minus 10. No good. Better to play it safe and play row 2. If he plays row 2, he gets a 0, which is break even, but that's better than getting the minus 10, which is what he'd get otherwise. Right. So you get the 0 here is the end result. Now notice something about this 0. This 0 is the minimum value in this row and the maximum value in this column. Right. Now notice that in the previous game, when we had our best strategy was both row and column stores choosing town 1, this 50 is also the minimum value in its row and maximum in its column. Now what's the significance of that? First of all, consider what it means to be the minimum in its row. Now suppose the row player chooses 2 and the column player knows it. Which column is the column player going to choose? He's going to choose the column with the 0 in it. Right. So if the row player chooses 2, the column player is going to choose this 0. On the other hand, suppose the column player chooses 2, which one is the row player going to choose? Well, the row player is also going to choose 0 because he knows if the column player chooses 2, he says, well, this 0 is better than minus 10. So in other words, if the column player knows the row player strategy and the row player chooses the column player strategy, they both agree on the same value. There's no guessing involved. It's the best for both of them. Of course, row player could get it better if he got this 5, but column player is never going to agree. And the column player could get better if he got this minus 10, but row player is never going to agree. So this is the best agreed upon value that they're both going to get. And as I said, it's the minimum value in this row and the maximum value in this column. Now there's another way to interpret this value. If I take the minimum value in this row, it's 0, and minimum value in this row, it's minus 10. Which is the biggest minimum value? Well, it's the 0. That's the biggest minimum value along the rows. On the other hand, what is the smallest maximum value along the columns? Well, the maximum value along this column is 5, and the maximum value along this column is 0. So this 0 is also the maximum of all the, the minimum of all the maximum values. Any other maximum value in any other column is bigger than this 0. So this 0 is called a maximin value as far as the column player is concerned. And this 0 is called a minimax value as far as the row player is concerned. So this 0 is the minimax and the maximin. It turns out that if that happens, you always have a saddle point. Now what's the significance of the maximin? Well, as I said, the minimum of a row is the smallest guaranteed value. All right, so if you have the maximin I'm sorry, I shouldn't say the smallest guaranteed value. It's the minimum row is a guaranteed value. If row player chooses this, he's guaranteed of at least 0. Okay, so this 0 is guaranteed value for row 2. This minus 10 is guaranteed value for row R. He's going to get at least this minus 10. Okay, it's not going to get worse. Okay, so if I have the maximum, that's the maximum worst value, maximum guaranteed value for the row player. He can't do any worse, and he could do worse if he played any other row. He could possibly do worse if he did any other row. Similarly for the column player, the min-max, right? The maximum value in this column is a 5, so conceivably he could get a 5. But the maximum value in this column is 0. He can't do worse than 0. Okay, so let me just explain that. I can say the min-max value, or let's see, max and min value along rows is the largest guaranteed minimum payoff over all rows. Okay. And the min-max value along columns is the smallest guaranteed max payoff over all rows. Okay. So if you have a saddle value, then the max-min and the min-max agree. Okay. Okay. And that's what we've seen here. All right, so they both will get their guaranteed minimum values. All right. So let's go on to the next example. As I said, saddle value, just review this definition. The Gij is a value that's simultaneously the minimum of its row and the maximum of its column. And if there is an entry in the matrix that has that property, that represents the option that both row player and column player will choose. The row player will choose that row and the column player will choose that column. Now it turns out there can be more than one saddle value. Let's look at this example here, which is a little bit more complicated than the original city example, where you have 3 towns and 2 stores locating in the 3 towns, and each store will get the business from the closest towns. Now if both stores locate in the same town, they'll split the business evenly. But for instance, if the row player locates here and the column player locates in town 3, all right, so let's think about that. If row player locates here, town player locates in column 3, what happens? Well, of course, the people in town 1 go to the row player store. People in town 3 go to the column player store. Who goes to, where do the people in town 2 go to? Well, they're going to go here because this store is closer than this store. So the column player is a loser because he only gets the people in his town. Everybody else goes to the row player. Right? But suppose, on the other hand, the column player located in town 2. So row player here, column player here. If the column player is here, where are the people in town 3 going to go to? Well, they're not going to go here. That's 15 miles. They're going to go to the closer store. Right? So in this case, if the row player locates in town 1, column player locates in town 2, the 2 stores split the business 50-50 because town 2 gets all the business from town 3. Okay. So you kind of get the idea that 50-50 is going to be the best option, and there are multiple ways of getting it. And if we get the payoff matrix, you can see here, notice that on the diagonal of the payoff matrix you get 50s. That's because if both stores locate in the same town, they're going to get half the business. But on the other hand, if store R locates in town 2 and store C locates in town 1, he's still going to get 50%. And similarly, if store 1 locates in town, store R locates in town 1, store C locates in town 2. All right? So you can kind of see from here, it doesn't really matter whether store R locates in town 1 or town 2, he's still going to get 50%. We can check that by looking at the saddle values. Look at this 50. This 50 is the minimum in this row and the maximum in this column. But so is this 50. It's the minimum in its row and the maximum in this column. And so is this 50. Minimum in its row, maximum in its column. So is this 50. All these 50s are saddle values, and they all are the same value. Okay. Since it doesn't really matter, you could just flip a coin. So there's really more than one optimal strategy. We could choose store 1 all the time, store 2 all the time, or we could flip a coin, choose each half the time, or you could throw a dice and go to town 1 if you get a 1, and go to town 2 if you get 2, 3, 4, 5, 6. So any combination of those two is going to be optimal strategy. Now the way you represent strategies for the role player is as a row vector. This 1, 0, 0 represents the strategy. Well, I always choose store 1. Now this strategy here, A 1 minus A 0, represents the strategy. Well, A% of the time, randomly, I choose town 1. And then, I'm sorry, I shouldn't say A%, I should say a fraction of A of the time, where with probability A, I choose town 1, and with probability 1 minus A, I choose town 2, and I never choose town 3. Right. So for the column store, we represent strategies as column vectors. So the column store could always choose town 1, could always choose town 2, or it could choose some combination of the two. The column player could choose town 1 probability A, and town 2 is probability 1 minus A. And that's still going to be an optimal strategy. All right, well, let's do another example that's a little bit bigger and see how this works. Here's another game matrix, and you can look through this and find the saddle values. For instance, this one is the minimum in its row and the maximum in its column. This is a saddle value. It turns out that there are several saddle values. This one is also saddle value, this one saddle value, and this one's saddle value. So player R could play any combination of strategy 1, strategy 3, and player C could play any combination of strategy 1, strategy 3. Right. So that means that player 1's optimal strategy can be expressed this way. A, 0, 1 minus A. That means with probability A, he chooses strategy 1. Probably 1 minus A, he chooses strategy 3, and he never chooses strategy 2. For the column player, it's similar. You have A, 0, 1 minus A, 0 means with probability A, he chooses strategy 1. With probability 3, 1 minus A, he chooses column player strategy 3. Okay. Now, so far we've talked about only strictly determined games with a saddle value. You can verify for yourself that these games do not have a saddle value. For instance, this one, the minimum in this row is 0, but that's not the maximum in this column. So this is not a minimax value. The minimum in this row is 0, but that's not the maximum in this column. So none of the minimums in the rows are maximums in the columns, so there's no min-max value. This game is not strictly determined. And you can do the same exercise for this one. The minimum of this row is -2. That's not the maximum for this value. Minimum for this row is -5, which is not the maximum value. Minimum for this row is -1, which is not the maximum value in this column. So no min-max values. This game is not going to be strictly determined. Okay, that's it.